since we've talked about a little bit about what chemistry is all about, well, first of all, we need to start at the basic level, right? Which, for the most part, is atoms. Now, of course, we've done atomic structure before in science classes, so this will mostly be a review. So, an atom is the smallest particle that maintains an element's identity, that keeps the same traits as all the other atoms of the element. If you break it down any smaller, it loses the element's identity. Now, the atomic theory has been in development for almost 2,500 years. As early as 400 BC, Greek philosophers were theorizing that atomos, well, the particles they called atomos, made up all reality. And Democritus was famous for claiming that atoms had different sizes and that they were constantly moving and that in between atoms there was empty space. Now, Aristotle, on the other hand, decided to pull the four elements theory out of thin air, and this was dominant for 2,000 years. And as was later discovered, many of Aristotle's things were far more wrong than his contemporaries. They just sounded more comfortable to the ignorant masses. And then there was the alchemists. So from the 1st century AD onward, in Europe, people were obsessed with creating stuff like the philosopher's stone, which was supposed to turn ordinary metals into gold. Or alternatively, creating recipes for immortality. Now, in China and other parts of Asia, this has been going on for centuries already. However, these equipments eventually became the equipment we know today, and the procedures for handling hazardous materials were tested out basically by if you did it wrong, you died. If you did it right, you're still alive, and you pass it on to your students. So, after some brutal natural selection, in 1808, well, as the 19th century approached, the atomic model gained more significance. Why? Because it became more popularly accepted, especially after almost all of Aristotle's other stuff had been debunked centuries earlier. So in 1808, John Dalton proposed the billiard ball model, in which atoms were solid and indivisible. So, like billiard balls. If you've ever played on a pool table or a billiard table, it's like you have a long stick and you have to hit the white ball and make it hit the other ball into the holes, right? I mean, I'm sure you've heard of this. So, 1897, we have J.J. Thomson. He discovers the electron. Well, he used the cathode ray tube to do it, and he noticed that, hey, wait, these are negatively charged particles. Really small negatively charged particles, and they have very little mass. So, what happened next? Well, he decided, well, they must be inside this atom somewhere, so why not like a chocolate muffin, or as he called it, the plum pudding model, which was basically to have these like little raisins in a plum pudding. Now, in a more modern context, chances are we would have called this the blueberry muffin model or similar. Now, a few years later, Ernest Rutherford discovers the nucleus. How did he discover it? Well, he used a particle beam. And I believe he used gold foil, or other samples were repeated, and he got the same results. So here, most particles went straight through. Straight through. Now, they knew that the particles thrown off by this radiation source were positive. And this was alpha radiation, which means it's positive and rather large. It's a helium nucleus, basically. So, they knew that these particles had considerable mass, so to deflect them this much meant that there had to be something massive and positive. And what does it say that most of this just goes straight through? Well, it says that bounced. It says that most of an atom is nothingness, empty space. So, what did he conclude? He concluded that the atom had a large positive nucleus. Well, large in terms of mass. Why? Because the way he described it, the electrons orbited around the nucleus. And the thing with this model is that you should take note of how small the nucleus is compared to the rest of the atom. How small is it? Well, if the atom was the size of a large stadium, like, arena for sports, then the nucleus is roughly the size of a typical ant. Pretty small, right? So, the vast majority of the space is empty space, and so most particles go straight through. A very few bounce and hit the detector elsewhere. So, he proposed a proton in 1920 because he realizes, hey, wait, if electrons are common to all atoms, then why can't the nucleus also have particles that are common to all atoms and which balance out the charge of the electrons? And he also realized, hey, wait, different nuclei have different masses, because they already knew the electrons were very low in mass, and they knew the nuclei were massive in mass. But these masses differed, so there must be a different number of positive particles. Now, 12 years after that, James Chadwick, who is not often remembered, is the discoverer of the neutron. And subsequently, Niels Bohr proposed energy levels. How did he do this? Well, this is hydrogen gas, so they used a little bit of electricity through gas at low pressure to excite the electrons in the gas. And when the electron goes up to a higher level and then falls back down to a lower energy level, it emits wavelengths of light that have the correct energy. And what does that mean? That means, oh look, this is falling from, say, level 3 to level 2. Let's draw a little diagram. So, hydrogen has a proton in the middle, and then it has, say, several energy levels for electrons. Well, then falling from level 3 to level 2, because the fall to level 1 is very large. This is not to scale. So the fall to level 1 is very large, and that would produce ultraviolet rays. But falling from level 3 to level 2 gives you the lowest energy separation. So that's the lowest amount of energy released. That's the red line. And then falling from level 4 to level 2 gives you this line. So it's a higher energy release. I mean, the difference is higher, right? I mean, if you drop a turkey from desk level on your foot, you will probably only crack a few bones. Whereas if you drop a frozen turkey from a freezer onto your foot, well, you had better be ready not to walk for the next month or two at least. So, clearly, this is very different. I mean, even dropping a nut, like this thing, from 50 floors is enough to kill somebody. Whereas, you can probably figure out that I'm not dead yet. So, the point is that, say this is level 4 to level 2. This is level 5 to level 2, and this is level 6 to level 2. Alright, so because he discovered these energy levels, we now concluded that electrons would fill up different energy levels. So what happens when you take the periodic table and mix it together with this? Well, we'll find out in just a moment. Alright, so let's go over some definitions first. Okay, electrons, negatively charged particles. These are very small and very low in mass. And they occupy mostly empty space around the nucleus. Nucleons are both protons and electrons. So, a proton is a positively charged particle, and it's in the nucleus. A neutron is neutral, and it's in the nucleus. Now, you might be thinking, hey, wait. If protons are all positively charged, why does the nucleus stay together? Well, that's because of the strong nuclear force, which is covered mainly in physics. Now, an energy level is a space around an atom where electrons exist, also called electron orbits. As you can see, this atom here has 2 energy levels. And let's take a look at how many protons it has. It has 3. So which element is this? This is lithium. Or, depending on preference, you can call it lithium-7. Or lithium-7 with a superscript. Anyway, for a valence shell, that's which layer here? Oh, it's the outermost one. So there's only 1 electron here. So how many valence electrons is this? 1, right? Alright, so what do we call this diagram? We call this a Bohr-Rutherford diagram, or sometimes just a Rutherford diagram. Now, sometimes when you have to do very large atoms, like say 77p, and there's a whole bunch of electrons, and drawing them all out would be too much trouble, sometimes Rutherford diagrams look like this. So something p, something n, and then you write, say, 2e minus, 8e minus. Sometimes you don't even write the e minus, depending on your country. And then 8e minus, 2e minus. Now, you will realize very soon that this doesn't quite seem right to you because of how the 3rd level is supposed to be able to take up to 18 electrons. However, orbital levels, as you will learn later, probably in AP chemistry or college level, orbital levels are split into sublevels. And when they're split so finely into sublevels, they can end up having the sublevels of one overlap with the sublevels of another. The lowest sublevel gets filled up first, which means that after this 2e, we start filling up this, up to 18e. What would that filling be? That's 10 different elements because there are 10 different proton numbers. That is the first row of the transition metals, which we will talk about shortly, i.e. in another section. So, atomic number and mass number. Well, atomic number matches the number of protons. It also gives the identity of the element, like how the element will behave in general. Mass number, on the other hand, is the number of protons plus the number of neutrons. And mass number tells you, well, it slightly affects reactivity. However, the effect is almost negligible compared to the atomic number. Mass number will also tell you a fusion rate, which is important when it comes to enriching uranium for use in nuclear reactors or weapons. But most commonly, mass number is just used to just designate which isotope it is, right? I mean, it's like saying, what is the most common use of food labels? To tell you what food it is, or what level of what food it is, right? I mean, okay, eggs. Oh, what's the most common use of the label on the box of eggs? To tell you if it's large eggs or medium eggs or extra large or whatever, right? So, an atomic mass unit is a small unit of mass that chemists use and it is equal to 1/12 the mass of a carbon-12 atom. Now, the unit symbol is U. You will learn quite soon, if you're also doing physics, why the one proton of a hydrogen atom has more than one U. It's something called binding energy, and that's in physics. So you should check out our physics videos. Now, in summary, atomic theory has evolved many times over the past 2,500 years. The Bohr-Rutherford model shows electrons orbiting the nucleus. Now, this model helps us predict physical and chemical properties for an element. Why does it do this? Well, it could help us see how many valence electrons there are. So if we know the valence, then usually that tells you a lot about elements' reactivity, as we'll see when we come to the section about the periodic table. So, the atomic number of an element is the number of protons. It gives the identity of the element. The mass number tells you, well, how many neutrons there are. It affects reactivity slightly. It affects a fusion enough to matter, i.e. when they're doing nuclear enrichment. And, well, for the most part, it also affects stuff like radio dating and, of course, stability. Why does it affect stability? Okay, so you might have heard of carbon dating. You probably should have heard of carbon dating. Carbon-12 and carbon-13 are completely stable. Carbon-14 decays over time. So, why does it decay? Too many neutrons. So, an atom can be represented in 3 different ways. Let's see. So, for lithium-7, we had lithium-7. We had lithium-7, and we also have 7 for lithium. And for carbon-12, it would be C12, C12, or 12, 6, C. So these are the 3 ways you represent a given atom, or a given isotope, depending on perspective. Now, of course, you could draw diagrams and such, so those are more than 3 ways, but verbally and in text, these are it. You can probably figure out that if you don't have a tool that enables you to use formulas in writing, this is probably the most convenient. Now, an atomic mass unit is defined as 1/12 the mass of one carbon-12 atom. One proton or neutron has a mass greater than this, greater than 1 atomic mass unit. Why? Well, okay, look at our physics stuff. We talk about binding energy there, not here in chemistry. In chemistry, we don't really care too much about nuclear reactions. In chemistry, it's mostly the stuff about the electrons and their interactions that we care about. Well, that's it for this section.